All right, happy Thursday, week two. Today is the last of the new material that will be on next week's test. So next week's test goes from chapter one through chapter four. There is a review document in this week's materials, but it's not required. It is just there for you to practice if you'd like. Probably the best practice that you're going to get would be going back through old homeworks. You can still do them in practice mode. So you won't get credit for them, but you can still go through and do practice work on them in practice. So that's probably the best way to practice. And I respond to messages fairly quickly most of the time if you have questions on any of the questions in your homework or on the review. Next Tuesday will be a drop-in office hours for an hour, be from 5:30 to 6:30. We'll have drop-in office hours. I will not be teaching any new material. I will be there for you to pop in and ask me any questions on the review or on the homework, and then or the lab, and then pop out or stick around and see if other people have questions. Sometimes there have been times when I've sat there the whole time, the whole hour with nobody showing up. There's times when I've sat there for the hour and had many, many, many questions and taught for the whole hour or helped for the whole hour. I I'm there for an hour regardless. So whatever you want to do, I'm there for you. That is my office hour next Tuesday. I will, in my Sunday email, I send out the Sunday emails. In the Sunday email, I'll mention that and I'll also put a note on the Zoom meeting, like where we click the link to get into the Zoom meeting. So you don't need to put it in your noggin right now and remember it. There's already a lot of stuff in there. So today's is one of my favorite lessons because it is probably the topic I've used the most. And I love taking a look at things and seeing if they're correlated with each other. And it's pretty interesting to me, and I've used it a lot. So chapter four is all about scatter diagrams. It's about correlation, determining if two things are correlated. It is about it is, we're going to learn something called the correlation coefficient, and we're going to determine whether a linear relationship exists between two variables. We are not going to do any other kind of relationship in this class. If you go on to Math 240, Stats 244, then they will jump into things like exponential and logarithmic and all of that stuff, and maybe even cubic and quadratic. And those are so super fun, but we're not doing them. We're just going to do linear relations in this class. And we're going to talk about correlation and causation. I'm going to show you a really fun website that is completely useless, but just kind of funny and makes me laugh. So I'm going to show you that. And we're going to find the least squared regression line. So I kind of changed last term. I changed the way that I teach this a little bit, but I didn't change my PowerPoint. So it's going to look slightly different than the PowerPoint, but you'll roll with it and it'll be fine. And then afterwards, we're going to do lab three. Lab three is super fast once you get your data. So that is tonight, and we'll probably be done earlier than the past three classes because this is the last of the new material on the test. So we might have a nice Thursday evening with so you can just get work done, and I'll make sure to check in a couple times for messages. But so you might just be able to get your lab done and just have it over with. All right. So before I jump into this week's material, I had promised you on Tuesday, or today's material, I promised you on Tuesday I was going to go through the one variable statistics and tell you what each and every single thing meant. But I forgot to do that at the end of Tuesday. So I'm going to take the data that I already had in my calculator. This is those test scores, and I'm going to go through each and everything. So if you want to, I don't know if you still have Tuesday's notes in front of you, but if you want to write down what each thing is, I'm just going to kind of add on to the end of your Tuesday notes. So go to my calculator. So remember on Tuesday, I taught you the one variable statistics. So you go into stat and then edit, and you can put all of your data in your list one. All this is the test data. It's still in there from Tuesday. I didn't mess with it, so it's there. And then to get to the one variable statistics screen, I'm going to hit stat, arrow over to calc, and one var stats is your first option. So I want list one. It's already there. Leave frequency list blank, and then calculate. All right. So this is the screen. I only showed you a couple of options on here, and I'm going to talk through what each thing is. Many of them I've never used. And I'm going to write them down on my other screen as we go. But you're not going to see it, but I'm going to write them down. That way you can kind of check your notes afterwards. So the first thing is X bar. We've already talked about this. The X bar here is 79. That is just the average, the mean. And if the calculator doesn't differentiate between sample mean and population mean, but we calculate them the same. So it just uses X bar. It just assumes we're using a sample and it gives you that. So this is just the mean of your data. So the capital sigma X, the next one that says 790, all of this is it added them all up. This is just all added together. And I pretty much never use this. I don't think I've ever used this, but that's what that is. That is just add it all together. The capital sigma just means add them all up. The next one, I bet you probably could guess this. This is adding up the squares. If I squared each
The
number,
screen phrases, right?
was that?
Okay.
Okay. So you just square, if you squared each number and then added all those squares together, that's the second one or the third one. And I've literally never used that. 6337. Don't know what happened. It says it's recording still. I'm going to reshare my screen. Did I go away and come back?
Yes. Yes.
Kind of.
Yeah, I don't know what happened there. Okay, I didn't know my screen was frozen either. Hopefully it's still recorded well. Okay. So, okay. So the third one is all of them squared and then added up. So the next two are important. Okay. The next two are important. Am I still muted or am I good?
You're good.
Okay. So SX is the sample standard deviation. That's the sample standard deviation. So this one is divided by n minus 1 instead of by n. And then the next one, the sigma x, is the population standard deviation. Guess my computer just decided it didn't want to play anymore there for a second. Or maybe it was too hot in here. Who even knows? Okay. So the next one is just your n. It just tells you how many there are. It is just how big your sample is or how big your data set is. So I'm going to write size of data set. Okay. I'm going to scroll down. And these are exactly what they look like, the next five. I'm not even going to write those down because I think those are so self-explanatory. So we have the minimum, which is our minimum value. You have Q1, which is your quartile 1, median, MED is median, Q3 is quartile 3, and then max is the maximum value. So you have your 5-number summary right there. These numbers right here, that is your 5-number summary. You don't even have to do any calculations. That's your 5-number summary. It is nice and lovely that they just put that right there for you, but it's there. So any questions on those items before I move on to today's information? Okay, so I'm going to go back here. I just wrote them all down. You can check my descriptions to see if they match what you wrote. And then we'll move on to today's informations. Okay, we're good? All right, let's move on. Okay, so we need a little bit of vocabulary here because this is going to feel kind of detached from the other things that we've done, but it all comes together in the end, but it's super important stuff. So the first thing is the response variable. So long time ago in the land of algebra, we learned about dependent and independent variables. The dependent variable was usually your y-axis, and the independent variable was usually your x-axis because the y-axis can't happen without the x happening. So like miles per hour. If hours don't pass, I haven't traveled any miles. So miles would be my dependent variable. It's the thing that happens because hours have passed. Hours would be my independent variable. The hours are passing whether or not I'm traveling. So the hours can happen all on their own. They aren't caused by something else. The miles happen because the hours passed. So the response variable is the dependent variable. It is the one that happens because something else changed. It can be explained in terms of the independent variable. It is not always going to be clear. Sometimes you just choose. Sometimes you just decide, hey, I'm going to decide that this one is my response variable and this is the explanatory. The explanatory variable is also known as the predictor, but I almost never see it called the predictor. Almost never. So the explanatory variable is your independent variable. This would be your x value. It's on the horizontal axis. This one is the one that causes the response variable to happen. This one, um, it's not dependent on something else happening. So this is your explanatory. This usually is the one that is like drives the bus, is usually how I say it. This one drives the bus. The explanatory drives the bus. The response goes along for the ride. So we use a scatter diagram. You've probably done this in your previous math classes where you're plotting coordinate points on a grid. That's what the scatter diagram is. It's going to show the relationship between the two variables, and these are always going to be quantitative. They're not necessarily going to be continuous. They can be continuous or discrete, doesn't matter. But every data set, so every X, Y combo is a point on the scatter diagram. All right, any questions on the vocabulary, or are we good?
Good.
Okay. So we're going to use this data. We're going to use it a few times. This shows a study for drilling rock. So what they're trying to figure out is how long it takes to drill 5 feet based on how deep they start digging. So how long does it take based on how deep they start digging? So the thing that drives the bus is how deep they start digging. So that would be my explanatory. So this one would be my explanatory. And then this would be my response. Because if I don't start digging, I'm not going to dig 5 feet. So the depth at which drilling begins determines how long it takes to dig 5 feet in this case. So what does it want me to know? Oh, that's all it wanted to know. Oh, no, it didn't. So we're going to draw a scatter diagram of this. I'm going to show you a scatter diagram. We're going to draw our own in a minute, but I'm going to show you what the scatter diagram looks like. Here's the scatter diagram. So as you can see by looking at this, as my depth gets deeper, the time it takes to dig is also getting longer. In general, there are some that don't follow the pattern, and this is kind of the way it is in life. Most of the time, you don't have things that follow a pattern exactly. You have, like I drive to work 30 minutes every day when I work at Illinois Valley High School out in Cave Junction. Takes me 30 minutes to get to work normally. But if I leave at a different time, it's going to take me a different amount of time to get there because of traffic and whatnot. So, or because I feel like I'm in a hurry. But it's not always going to be the case. It's not always going to be the case. So there would be some that don't follow my pattern. But if you can, most important here, I'm going to draw a line through like the middle of my data. It kind of follows this trend. In general, as my depth gets deeper, the time it takes to drill 5 feet gets longer. You never know. They might have had a spot that had less rock in it, or maybe there were pockets, or I don't know. I don't know all of the mechanics in drilling holes, but you kind of get an idea there. All right. So this is the one that we're going to do on our own. A golf pro wants to investigate the relation between the club head speed of a golf club in miles per hour and the distance the ball travels in yards. So he's going to have club head speed and the distance the ball travels, but there are other variables that come into play. So that we're going to try to minimize those. So there's club type, ball type, golfer, weather conditions. There's probably even more. So to eliminate as much variability as we can regarding the other variables, he took the same model club, the same ball, the same golfer on a 70-degree day with no wind. So the rest of the outside influences are minimized as much as possible. He records the club head speed and then measures the distance the ball travels, and then collected the data in a table. So here's our data right here. So the club head speed is our explanatory variable because if we don't swing a club, the ball's not going anywhere. The distance in yards is our response variable because it responds to how fast you swing the club. So let's just plot these points. So let me get a good pen on here. So at 100 miles per hour, so my horizontal axis is miles per hour. My vertical axis is distance in yards. So 100, I'm just going to estimate. Most of this is going to be estimating where it is because not many of them are pretty numbers. So 103, 274. I'm just going to plot these things fully. Thankfully, there's not a lot of them. 5, 100. 63, 99, 258, 105, 275. All right. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. I missed one. 100, 263, 2, 3, 4, 5, 6, 7. I missed one. I don't know which one I missed, but let's pretend I have them all because I don't know which one I missed. I don't know. Okay. So you can see my data is plotted here all but one point, which I don't know which one I missed. And you can see that in general, as the golf club moves faster, the ball is going to go further. So it's possible that maybe he hit it off center, maybe he hit it, you never know what caused the difference. He probably, maybe he just didn't hit it square or whatever. But if I drew a line through pretty much the center of my data, you can see that it is a positive slope. Thinking about slopes from your algebra classes, it is a positive slope. It is getting more. And notice, compared to the last one, notice how they're more grouped around that line. So this one is more linear. This one right here, not quite as linear because you have some that are that are kind of far away from it. And you'll kind of see in a little bit the difference there. But this one right here is more linear because they're more grouped around that line. Any questions so far? Are we doing okay? We're
Doing good.
okay. Good, good. All right. So let's take a look at the types of relations that we get with the scatter diagram. So our vertical axis, of course, is the response, and our horizontal axis is the linear, is the explanatory. So these two, the top two right there are pretty linear. This one is almost perfect. This one right here, almost perfect. They're grouped around that line really well. This one, not quite as perfect. This one has a negative slope, but it is still linear. It's just negative. And negative is perfectly acceptable. It's still linear. So the one on the left is a positive linear relation. The one on the right is a negative linear relation. So look down at the bottom three. So the one on the left on the bottom is clearly a quadratic. It looks like a parabola. It looks like a rainbow, looks like a parabola. And so it is quadratic, but it is not linear. It's non-linear. So it does not have a linear relation. It has a quadratic relation, but we're not even dealing with that. So it is non-linear. And the second one, you may or may not know, is cubic. It is not linear, but it does have a relation. It's just nonlinear. So we wouldn't say that there's no relation. We would just say there's no linear relation. And the last one, there's no relation at all. I don't like it's not quite scattered enough, but it's just kind of all over the place. There's no relation at all. We still would just say no linear relation because that's all we're dealing with in this class, but there's really no relation there. It's just kind of a crazy, wild mess. So these two right here is what we are looking for. These are what we want to find. This is what we want to see if we can. That's what we're looking for. All right. So I already kind of mentioned this. When we have a positive slope, when as our x value gets bigger, our y value also gets bigger. There's a positive association, or it's a positive linear relation. If as our x value gets larger, our y value gets smaller, it's a negative linear relation. So just take a look at the slope. Take a look at what the slope is doing. And if it's going downward, if it's trending downward, or if it's trending upward from left to right, we read them from left to right. Trending upward from left to right is positive. Trending downward from left to right is negative. And that's that. I'm itching for the math. Love the math stuff. Math is my jam. Now I'm going to tell you this equation is this formula is crazy. I never ever will ask you to calculate this. Never. I had one person do it in their final project and it was kind of cool, but I don't recommend doing this formula in your final project, which couple weeks I will give you your final project. Probably week 4, I will give you your final project. Anyway, so the linear correlation coefficient, it measures the strength and the direction of the linear relation. Remember when we looked at the drilling data and how it was not as close to the line as the club head data. So the club head data had a stronger positive linear relation than the drilling data did. So if we were doing population, we would use the Greek letter rho, but we almost never use the population because if we had all the population, it wouldn't be as necessary. So we almost exclusively use the sample, which is just an R. We'll call it an R value. It's the correlation coefficient, but because that's a mouthful, we just call it an R value. So I'm going to tell you kind of what we do with how this works. I'm going to tell you what the formula is, but you don't have to actually do the formula. So what you do is you find the z-score of each x value and the z-score of each y value. So you're going to take the first ordered pair, take the z-score of the x, the z-score of the y, and you'd multiply them together. Take the second ordered pair, z-score of the x, z-score of the y, multiply them together. You do this with all of the data values, and then you're going to add up all of those products. Then you divide by n minus 1. I'm not asking you to do this, just kind of telling you what you do. And you get your R value, and it'll tell you the strength. And I'm going to explain what the strengths look like, kind of a rule of thumb, because there is no hard and fast rule. There's no like in stone, this is the rule. It's kind of like depends on how important what you're doing is, on whether or not on what numbers you use. Okay. This is a lot of words, so I'm just going to try to get through it without I don't want to just read to you. So our correlation coefficient, our R value, is always between -1 and 1. It can be -1 and it can be 1, but it is between those two numbers. You will never have an R value outside of -1 to 1. If you have a +1 R value, it's a perfect positive linear relationship. If you have a -1, it's a perfect negative linear relationship. The closer you get to 1 or -1, the stronger your linear relationship. So super close to 1 or -1 is very strong linear relationship. The next page. The closer we get to 0, the weaker the linear relationship. So thinking back about the drilling data and the club head speed, the drilling data is probably a lower number than the club head speed because it wasn't as tight around the line that I drew. The club head speed was all kind of, you could see the line in it a little bit better. It's closer to 1. We're going to actually calculate those in a little bit. So the correlation coefficient is unitless. It doesn't, we don't use any of the unit measures. It's just all it is telling us the strength of the relationship. And it is not resistant, which means it's kind of like mean and standard deviation. If you have outliers, it's going to drag that number pretty drastically. So outliers affect it greatly. So that's what I have to say about that. It's going to make so much more sense when we're actually applying it, as with everything. The words are there and they're great for after you already know how to use it, and then you can go back. But just kind of put this in your pocket and then pull it out once you know what you're doing. All right. Their measurements here are not quite accurate, so I'm going to fix a couple of them. The first one, letter A, that's a perfect positive linear relation. The R value there is 1. It is perfect. It is beautiful. You see it's a perfect line, perfect positive line. The second one, it's pretty strong positive. If I draw a line through it, everything's grouped pretty close to that line. It's pretty strong. It has about a 0.9. My correlation coefficient is 0.9. So it's pretty close. It's very strong. I'm going to give you, I'll give you kind of guidelines in a little bit. And they're very, very, they're not firm guidelines. They're fluid. You're kind of like, depends on how important it is. I'm going to have, it's going to matter more if I'm building a space shuttle than it is if I'm putting a garden in my backyard type of a thing. So you're just going to have to kind of use your best judgment. I don't like that this one says 0.4. This looks to me more about a 0.6. So I'm going to put 0.6 there. It looks more like a 0.6 to me. And I've been doing this a while, so I kind of trust my instincts. But so that one is about a 0.6. You can see that it trends upward. You can see that it's positive, but it's not super strong. They don't tightly conform to a line. If I draw, well, that's not even a good line. If I draw a line through them, they don't gather right near the line like the last one did. Letter D, perfect negative. That no explanation needed. Perfect negative. And it has a -1. Because it's negative, it has a -1 R value. Letter E, is that an E? Yes. Has a strong negative relation. It is pretty strong, but it is -0.9. Because remember, it's going downhill, so it's 0.9. And it is, once again, if I draw a line, if I draw a line, it's harder to draw the negative line than it is the positive. They're all gathered right around that line. Once again, this is about a -0.6. I don't like their numbers. It might be slightly less than that because of these. These right there might have dragged it down, but let's ignore those. I'm going to just erase those. Let's just erase those. There we go. Now we're at a 0.6. I just erased them. So letter G, you could see that letter G, you can see a kind of a pattern, but it's not linear. It's really close to 0. It's probably going to be something like 0.12 or something. There's pretty much nothing. I would say maybe -0.12. It looks probably more negative than positive. If you can't even figure it out, it's probably pretty small. Letter H, you can see that it's a quadratic, as with that other one. It's like this nice upside down rainbow, but it's not linear. It's not linear, so therefore it is close to 0. Questions on these before I give you kind of the rule of thumb. Okay. So these are not set in stone. These numbers are not set in stone. They're just kind of what I use. So if I had something, and this applies like for negatives and positives, I'm not going to do both of them. If I had something probably like 0.85 to 1, or maybe 0.99 because 1 is perfect. I'm going to say that these are strong. These are strong. It's a strong linear relationship. This is strong. Now, if I'm going, let's say that I'm 0.75 to 0.84, I might say this is moderately strong. Remember, we love adverbs. We do not deal with absolutes. Now, if I go from, let's say, probably 0.5 to 0.74, I would just probably just call it moderate and not even moderate, not put words like strong or weak or anything because they're kind of related, but they're not super related. 0.5 might even be a little bit too low. Now, if I went from let's say 0.35 to 0.49, this would be moderately weak. Then about 0.2 to 0.34, this is just weak. Anything 0.19 and under, it's very weak or no relation. No linear relation. So while you're writing these down, now if I was building a space shuttle, I would not accept 0.85 as strong. I would want it to be like 0.95 or greater, right? Because it's important, lives are at stake. If I'm putting a garden in my backyard, I'm fine with 0.7, probably even 0.65. So it really depends on how important it is. And I'm not going to be a stickler. Now, if you told me if you had 0.74 and you called that moderately strong, I'm totally going to take it. But if you had 0.8 and you call it weak, now there I'm going to have issue. So as long as you're in the ballpark, you'll get all full credit on it. I'm not going to be a stickler about that. Just be in the ballpark. These are not set in stone. This is just kind of a guideline to give you an idea. And you can use your own words. These are just my words. So you could even use your own words there. The only place that you're going to really be typing it out is going to be in your lab, and you're going to kind of make a judgment call on your own data in your lab. Otherwise, I'm going to give you things to choose from, and you're just going to match things with each other. So, questions on this before I move on? All right. If I flinch, it's because my cat is attacking my back right now, and occasionally her claws come out. So if I'm flinching or cringing, it is not you guys. It is my cat. She's being silly. She is fully recovered from surgery, obviously. Okay. Yes, she's a crazy cat. All right. So we are going to be using your fancy calculator. So you are, I'm not making you determine the correlation coefficient without the calculator. We are also going to find the line of best fit, and we're going to do that at the same time. Okay, so I'm going to go to my fancy schmancy calculator. Here we are. Hopefully you have yours available. We are going to go into lists again, where we were before. So click on Stat and Edit. I'm going to clear out my list one. Now my X value is going to go in list one. My Y value is going to go into list two. So I'm just going to type those in there and go ahead and type them in with me and beware of typos. Ninety. 1, 2, 3, 4, 5, 6, 8, 9, 10. Hey, okay. I'm gonna give it a second, let you guys finish. My top two are not showing. but give you a second. I'm going to go over to the y value. Uh-oh. These ones take a little bit more thought because they have decimals. Really important after you put these in there, check and make sure your numbers are lined up because they're each an ordered pair. The two things next to each other are an ordered pair. So if you don't have them lined up correctly, bad things happen. I only say it because I've done it numerous times. I'm always happy when I end and they matched up. Okay, give you a minute. Right, does anyone need more time? Are we good? All right. Okay, so once again, we're still going to go in the same place we were before. You're going to hit Stat, like we were before, and go over to Calc, and we're going to number 4, linreg AX plus B. So it's a linear regression, AX plus B. The AX plus B is kind of like, I'm sure this will ring bells, Y equals MX plus B from algebra class. It's a line, so it's Y equals MX plus B. So we're going to go down to number 4 and hit Enter. So our X list was in L1, our Y list was in L2. I frequently will have multiple data sets in my lists. So maybe you're using 3 and 4. Once again, you hit the blue button, which is second, and you would do second 3 for L3, and then second 4 for L4 if you had different lists. Because sometimes if I'm working with multiple things, I will use my other lists. The frequency list is going to stay blank. We're not this right here. What this is for is storing the equation into your calculator so you can graph it and do other things with it. We are not storing it. And then go down to calculate and hit enter. All right. If you don't have, if you are missing the R squared and the R, we're going to have to do some magic stuff in your calculator. Is anyone missing the R squared and the R in theirs? Okay, but for those who are watching that might be missing it really quick, I'm going to show you how to do it. You two just sit there and look pretty for a second. So if you're missing the R square and the R, we just have to turn on a program in your calculator. It'll do second 0 because see it has the word catalog above it. So second 0, and then scroll down to the words diagnostic on. So I'm going to scroll all the way down here to diagnostic on. You hit enter and then enter, and it says done. So it's turned on. And then when you go back there, it'll be there. Mine was already there, so it's going to be anticlimactic, but it will be there. All right. So let me explain what things are here because we're going to do two things at once instead of doing it later. So the R, this is the R value. I'm going to write this down on my my notes right here. This is the R value. So my R value is 0.66. So it's moderate. It is not very strong. It is moderate. And this is the drilling data. And remember we said that it didn't look like it fit with the line really well and it was probably lower. This is a lower number. It's 0.66. So it's pretty moderate. The A value here, this is the slope of your equation. So y equals mx plus b. This is the m. So notice right here it shows you y equals ax plus b. A is the slope. B is your y-intercept. So if you were to graph it, it would cross the y-axis just right below 6, and it would have a slope 0.0096, etc. So if I'm writing the equation of this line, and I'll explain what the line is in a minute. If I'm writing the equation of this line, I would write, and I'm going to flip to the other screen in a second, y equals 0.00, I'll just do 96x plus 5.86. This is, remember the line that I drew through the data, like through the center of the data? That is the equation of that line. It is the line that fits the data best. So what the R squared is, this is called the coefficient of determination. And I don't believe that you have to use it at all, but I kind of want to explain what it is. And you're not going to be tested on it at all, but I just want to let you know what it is because it does hang out there. So what it tells me is that 44% of the variability in the time it takes to drill 5 feet can be explained by this equation. So 44% of my Y value can be explained by this equation that I created. So this is telling me that I probably don't want to use this equation to make predictions because it's only going to be about 44% accurate. So we probably don't want to use it. That's basically what it is. All right, I'm going to pop over to what I've written right here. Any questions on this so far? Right. We're going to jump to the club head data. Okay. I would like you, I'm going to find my calculator while you start working on this. Would like you to put this list in and run your own linear regression. If you get stuck, it's okay. You can sit there and look pretty until I do it. I just got to find out what I did with my calculator. Oh, I plugged it in. I'll be right back. So remember, stat edit, and you're putting these in L1 and L2. See how you did it? Okay. I got, I'm just going to write down mine. I'll be quiet and so let you get yours. How'd we do? I rounded. Okay. Edith, how'd you do? You got it? Okay, good. So this is a really strong correlation. I'm hoping that you saw this and were like, yes, that's nice and strong. That's very strong linear relationship because it is in the nines. Anything in the 0.9s is going to be a strong linear relationship. This is positive because as my X values get bigger, my Y values get bigger. If I look at my R squared value is 0.88. So this is telling me that 88% of the variability in the distance the ball goes can be explained by this equation. So 88%. That's a coefficient of determination. So I can probably make a decent prediction. However, unless you have a perfect linear relationship, you always have to be cautious if you are using data that's like far away from yours. So I probably wouldn't use this for 125 mile per hour club head, but I would definitely use it for 106 or maybe 108. But I wouldn't use it. The further away from your data you get, the more likely you're going to be kind of off. So you don't want to use it too far away, if that makes sense. So this is my equation, so I could use it to make predictions. So if I wanted to say, okay, well, I want to know how far would we expect the ball to go if I had a club head speed of 106. I would just plug 106 into that X value and math it out, and it would give me an answer. So I don't believe that we ask you to do that in your homework, but I just want you to know that you can do this. And so it's super, super useful. All right. Questions before I move on? Okay. So, an important thing that we need to talk about, and I'm sure you've heard before, that correlation doesn't equal causation. So, this means that even though things are super correlated, you can't necessarily say one thing caused the other. So the only time that we can assign causation is if we did an experiment where I'm sure you remember when we did the batterer treatment program. That was an experiment where we actually had a control group and we performed an experiment and we were able to compare those two things. So when we applied a treatment to something and then have a control group, then that is not observational data. Observational data is when you watch something happen and then you say, oh, well, that thing caused the other thing. You can't do that. So correlation doesn't equal causation. So the correlation between teenage birth rate and homicide rate since 1993 is 0.9987. That's almost perfect. But you can't say that higher teenage birth rates cause the higher homicide rate because this is observational data. You can't say that. I'm going to show you the fun website because it is super fun. Let me get rid of this right here. Okay. So there's this website called tylervigan.com or spurious correlation, and there's a lot of things that are super correlated that just are so funny. Like this one right here. The popularity of the first name Annabelle correlates with UFO sightings in Maryland. This has an R value of 0.962. So they're super correlated, but one thing did not cause the other. All right. So burglaries in Oklahoma corresponds with the first name Christopher. So as the name Christopher became less popular, burglaries in Oklahoma went down. So don't name your kid Christopher unless you want those burglary rates to go up. So it's 0.966. There's a ton of them here. This whole website is just full of them. So popular of the first world problems meme, Google searches Vihart. I don't know if you know who Vihart is. She is this really great math video person. She's fantastic. That's 0.98. See here. So vinyl album sales of vinyl albums and Costco's stock prices. See here. Bachelor's degrees awarded in education and the number of proofreaders in Kansas. Now this one, you never know. There could be some causation there. Popular name, the name Lamont and burglary rates in the US. Okay, where's some good one? Judges, number of judges in Indiana and viewership of The Big Bang Theory. There are hundreds and hundreds of them. You can even create your own. It's a super fun website. I will write it down just in case you want to play with it. There's a place where you can do your own, and I don't remember where this is. I think it's like at the bottom. I'm not sure where he is. Discover a new correlation right there. This is where you can do that. And it's super fun. So you just scroll down to the bottom and go to discover new correlation and you can create your own. It's just a really fun page. I actually have a printed book because it's so much fun. Okay, I'm going to write it down for you just because, hey, why not? It is tylervigan.com. Or if you just Google spurious correlation. It'll get you there. It's just super fun. Anyway, so that's my correlation doesn't equal causation soapbox, and there you go. All right. So some important things here is lurking variables. So sometimes there is a variable that will affect both the explanatory and the response, but it is not included in the data set that you're analyzing. So it kind of gives you this false correlation. So I have an example here. So it gives you a false, identifies this strong relation between two things, and it doesn't really show the true relationship. So here's an example. And air conditioning bills increase. As air conditioning bills increase, crime rates also increase. So turning off your air conditioner is not going to combat crime. The lurking variable is the air temperature. Both things are correlated with the air temperature. As the temperature increases, crime rates increase and air conditioner bills increase. So those two things are both connected to air temperature. So air temperature is that lurking variable. So it's just something important to kind of think about. Are there other variables that are affecting things? These are not something that you're going to be tested on, but this is important stuff to think about, especially as you anybody that's going into the medical field, especially. There's thinking about, is there a symptom that's going to cause both of these other things to happen? You need to think about those lurking variables or like a condition that could be happening there. It's medical field is probably one of the bigger things. We have had the same thing in the education field where we have to look for those lurking variables. Okay, so we've already done this, so this is going to be super fast. So the least squared regression line, LSRL, or the line of best fit, it is that line that we came up with. It is the line that fits our data the best. It minimizes the vertical distance, so it's the line that causes your data to most follow it. And this is the line of best fit. This is that y equals mx plus b line that we found. See, I just decided to include it in the earlier stuff rather than do it twice. Rather than run linear regressions twice, I just decided to already include it and then give you your definition afterwards. So this is the line that we already ran. So going back here, this right here is called a least squared regression line or a line of best fit. Or most will call it a line of best fit because least squared regression line is longer. The other way that we do it, we say LSRL, least squared regression line. Either way, I'm not sure what your homework calls it. I don't remember. Okay, go back. Go back. Okay, we already did this. We already did this. And guess what? That was slide 20. That was our last slide. I know, isn't that fantastic? Look, we're at 6 o'clock. I've only been talking for an hour. So before I move on to the lab, do we have questions regarding the material that I just covered? Okay, the lab should help a little bit with this also because the lab is using linear regression. Okay, let me jump to the lab. Where is it? There it is. All right. So in the lab, you were asked to find two variables that you think might be correlated with each other. So I took random basketball players. I took 20 random basketball players. And the thing is, I should have considered their position that they play because that'll make a difference on the points scored. But I didn't because I was just randomly choosing basketball players. Um, and then I took their height and the average number of points that they scored in this past basketball season, the average number of points per game. So I just took random basketball players, I took their height and the random number of points they scored per game. And I just put this in there. So this person right here, this 80-inch tall person, scored 16.2 points per game. So this is one ordered pair. So make sure that that ordered pair is one person and his information. So if you were doing like rainfall and barometric pressure, make sure that if you're doing that on one day, you have the rainfall from that day and the barometric pressure for that day. And then the next one would be a different day and the different barometric pressure. I just chose something random. All right. So we already know all of this stuff. So what's your population? What are the variables you're studying? I don't care about the interest. You don't have to be interested in it. What are the units of your data? So you should have 2 units if they have it. So my first unit is height in inches. And I don't know why they don't give me like zero point 0.5, like 79.5 inches, but whatever. And then points is, and then my other one would be points. And probably kind of no units, but it's points. Why number D, letter D? I want you to answer based on not before you do your scatter plot and find your R value. I want to know, why do you think that they have an association? I think taller basketball players would probably score more points. That's what I think. That's why I chose those two. I think taller basketball players would probably score more points. I'm just looking for an opinion here. On letter D, why do you think they're associated? That's it. You don't have to, we're not analyzing the graph that you haven't created yet. Letter E, where'd you get your data? I went to NBA.com. That's where I went. You'll go somewhere else or asking friends or whatever. So this is just, where'd you get your data? I asked 20 friends. I looked on the computer and I don't know, but Google's not a source, but the website you went to is a source. All right. So we can't answer F until we create our scatter plot. So I'm going to create my scatter plot. The one on the left is your X value. This will show up on the X axis on the horizontal. The one on the right is the Y value. It will show up on the vertical axis. So take a look. I'm going to highlight not the name, not the what my variable is here, just the numbers. And I'm going to go to insert. Recommended chart will probably have your chart. If not, you're going to choose this one right here or this one right here. But recommended charts will probably have it. That's the one I want. But this right here, you're going to choose this one. Don't choose any of these wacky things. Choose that one. There's some wacky stuff there. All right. Obviously, this is not ready for me yet. It doesn't have everything I need on it yet. It is just basic, basic. Okay. But it's pretty. Boy, this guy. Look at that guy. This not very tall guy. He sure scored a lot of points. Wow. Okay. Anyway, see that outlier there? I bet you that caused my R value to be small. I don't know what my R value is yet. This is new data. I had different data before and I just was bored with it. So anyway, I want to pick, you make sure that you do this part first, whatever style you want to do, you choose that first. Otherwise, it's going to disappear. Everything you do is going to disappear. So I just want a regular one, but I want colors. I like purple. Oh, that's orange. Let's go with purples. Okay. So do all of that first. So now I'm going to insert, go to back to here. I want to go to click on my chart. What in the heck? Chart design. Oh, I was in a weird spot. Sorry about that. Okay, I'm going to add chart elements. Here's the things I want. I want my axis titles. So primary horizontal, add a chart element, primary vertical. You need the axis titles. You're going to need the chart title. So I'm going to write here, right here. Remember this right here is height in inches. And then this one is average points per game. If I could spell. Points per game. And I need a chart title. Average, okay. NBA players points per game by height. Good enough. Okay. Okay, I got that. That's all. That's lovely. But I'm not done yet. I want the regression line. I want that line on there. So I'm going to go add chart element and I'm going to go to trend line. We are only dealing with linear, but I'm going to click on more trend line options because it's going to open this up. I want linear. You also want to display the equation on the chart and display the R squared value on the chart. I'm going to drag it. You can drag it wherever you want. You can change the font size, which I'm going to do so you can see what I'm doing. I want it to be bigger. There we go. You can change the color of it if you want. I could decide that it's going to be purple because who doesn't love purple? So you can change colors, you can change size, you can change the font, whatever you want to do, but that needs to be on there. So it does not give us our R value. It gives us the R squared. So it gives us the coefficient of determination. It does not give us the correlation coefficient. So we have to calculate that ourselves. So I'm going to go down here, and it doesn't have a spot for it. Someday I might fix that. I'm just going to type R equals in here and go to the box next to it. And I'm going to take the square root of my R squared value. So remember, whenever we're telling it to do math, you type in equals and then just SQRT. So you notice it's right here. And then I'm going to just type that in there, 0.0243, close my parentheses and hit enter. Now I have a correlation coefficient. Now, one word of warning here. If you have a negative correlation, if you have a negative relation, it's not going to show that there. It's going to be positive no matter what, because if I multiplied a negative times a negative, it gave me a positive. This is no matter what going to be a positive. You have to pay attention. See, I have a positive slope here, so mine needs to stay positive. But if I had a negative slope, I would need to mention down here that it's negative. So I want to know, how good is the association between my two variables? Mine's terrible. There's virtually no linear relationship between them at all. There's no relationship between height and points scored. I want you to reference what your variables are. I want you to reference your correlation coefficient, this right here. I want you to mention, is it strong? Is it weak? Is it moderate? What is it? I want you to mention that. I want you to refer to this right here. How do you know? How do you know it's strong? You can say there's a strong linear relationship between the shoe size and height of these people because my R value is 0.87 and that's pretty strong, yada, yada, yada. Or if you had a negative, you need to mention it. So I want you to talk about what your variables are, talk about the relationship between them based on your R value, and mention how you know. And that's it. This is actually pretty fast once you get your data. It just took a while because I talk a lot. So questions on this? Try to have fun with it. Find some fun variables. Try to have some fun. Now you only need 20 data values for each one. Okay, go ahead, Edith.
Oh, now I forgot I was going to ask what I was going to ask.
Sorry.
No, it's okay. I'm just asking, like, do you think it's helpful to have like a do this, do that, do this for, like, I mean, because I know you just remember what to do one step after another,
Huh?
but I don't remember the steps. And then I'm like flipping around trying to remember the steps. So in my notes, do you think it's worthwhile to go through and go do this when I'm trying to, get this result? Do this, this.
Maybe even, it doesn't necessarily need to be do this, do this, do this. You might just want to say, these are the elements that I need. So
Oh,
I need to make sure I have access titles. I need to make sure that um that the equation and the R squared are on there. So maybe rather than do this, do this, do this, have it be these are the elements I need to have. Because
okay.
these ones over here, these ones I don't think you really need notes on, right?
No,
These
I do.
down here. But like, what do I need on my graph? You might need notes on that.
Okay.
And
Thank you.
yeah, I think
Yeah.
that's probably makes more sense. Otherwise, you're going to have this 3 pages of notes, and most of them are not going to be
Yeah. And
important.
that's what I don't need because then I
Yeah,
won't remember.
it's
Okay.
overwhelming. Instead, just bullet points of this is what I need. These are the pieces I need when I'm done.
Thank you.
You're welcome. That was a great question. I've never had anyone ask that before. That was really great.
Oh, thanks.
All right. Anything else? Okay, so we're still on recording for any questions about anything in this lesson or not in this lesson while we're recording. Do we have any more? Right, I'm going to turn the recording off.